So let's use a little bit more complicated example of a multi-step mechanism and see if we can relate how the intrinsic rates of those elementary steps, in this case we have 3 elementary steps, relate back to that experimentally determined rate law for the overall net reaction, just as we did in the previous video. So here we've got 3 reactions. We've got some information about each that's sort of empirical, that's written on the right. So we have the first step, which we're told is fast and reversible. Fast means that it happens really quickly. Reversible means that the reaction can run in reverse as well. I have indicated in the actual rate constants, K1 being the forward reaction rate constant, and then the reverse being the rate constant in reverse. And I've indicated the fact that this is reversible because I have a double-sided arrow in this case. The second reaction we are told is slow and rate determining. That has a rate constant K2, and then the third reaction is fast again, and it has a rate constant K3. So pause the video here, write this out, and see if you can come up with what the balanced net reaction is based on the individual elementary steps that we have here. So I get something that looks like this. That's our net overall reaction that is comprised of these 3 individual steps, the first of which is bimolecular, second is bimolecular, and third is bimolecular. So based on the logic that we talked about in the previous example, we should be able to predict what we think the experimental rate law should be for the overall reaction that's written in pink, simply based on which of these steps is going to be slowest. So you can sort of think about the funnel analogy again, where the fast first step would be a wide open funnel. The second slow step would be a really narrow funnel, which constrains the flow of the fluid that's moving through it, and then we have a fast step. So we might hypothesize that this second step is actually going to be the thing that we observe in reality, because it's the slowest one. It's going to dictate the observation experimentally. So let's see if we can write up a rate law based on the second elementary step. So pause the video and see if you can put up a rate law based on that step alone. So using the logic we had before, we just look at this second step. We then write out rate is equal to the rate constant of that step, which is K2, times the concentrations of the individual steps to yield this overall bimolecular reaction, where we physically have to have each of these molecules collide with each other in space, which means that this is overall a second order elementary reaction step. But the reaction is first order in N2O2 and first order relatively in H2. The problem here that some of you may have realized in staring at this is our predicted rate law here includes this species N2O2, but if you look at our overall net reaction here, N2O2 is nowhere to be found. And that's really confusing, right? Because when you add NO and H2 together in a reaction flask, you are not including N2O2, but somehow our predicted rate law includes it. So how do we reconcile this predicted rate law, which includes this species N2O2, which we can say is actually an intermediate because it's on both sides of the reaction, they cancel out. How do we get that in terms of something that makes sense realistically for what's in the lab based on the experimental outcome? So the experimentally determined rate law, the one that you measure in the lab, looks like this. And I wrote it in terms of the formation of N2. That's the species right here, just because there's a 1 in front of this, and so it makes our stoichiometry easier. But I could have easily written this in terms of either NO or H2. I just would have had to incorporate a -1/2 here. The important thing is that the rate law that's experimental includes 2 species, but those 2 species are in the actual net reaction. It includes NO and H2. So how do we reconcile the predicted rate law based on the slowest rate determining step, but that unfortunately includes the species that's an intermediate, with the experimentally determined rate law? Well, we need to use a little logic. So let's think about these individual reaction steps and see if we can do some substitutions to make these things reconcile or work out together. So the first thing we can think of if we're trying to sort of relate these two expressions together is how does the disappearance of N2O2 relate to the creation of N2? Well, that's really just these two last steps. And what we know is that the second step is super duper slow and the third step is really super fast. So another way to write that is this approximation I have indicated here, which just says that the rate constant for the third step is probably a lot bigger than the rate constant for the second step. And that's simply because we know this one's slow and this one's fast. So what are the implications of that on the relationship between these two things, the disappearance of that species with the appearance of the other one, N2? Well, if this is super slow, then that means these two products are just trickling out, right? So as N2O2 disappears, which is what this elementary step is indicating, the moment that these things appear in the reaction flask, right here, they're going to very quickly proceed through the third step, which is, again, related to the appearance of N2. So this seems like a lot, so you might have to pause and rewind and watch this a few times. But the disappearance of this species is really slow, and then the appearance of this is really fast, but it depends upon that first step. And so these two things are directly linked, and we would be able to essentially say that the rate at which this thing gets destroyed pretty much dictates the rate at which this thing gets created. And so they're directly related to each other, and we can say that the rate at which that stuff gets destroyed. Remember, I'm using these dt notations, but you could equivalently use the delta notations. We're not really doing calculus. I'm just representing the rate at which they're created or destroyed. That must then equal, or we'll say approximately equal, the creation of that thing. So once we have that relationship, we know that's equal, we can do some substitutions, the goal of which would be to get rid of this N2O2 thing, because that's not in our actual reaction flask. That's not something that's real. It's simply an intermediate that we could never observe. So we can start by substituting that species in here because of this equality. And I can rewrite that like this, which is the same as what we had up here. Oops, I forgot the K2. Except now I've replaced the disappearance or the destruction of N2O2 with the appearance of N2, the rate of that appearance. Okay, so now we've gotten the disappearance of N2O2 out of this predicted rate law. Now we need to also get N2O2 out of that part of the rate law as well. So now we're in terms of N2, which is good because that's a real thing, but let's get rid of that. How do we do that? Well, we need to go back up and use the very first reaction, the elementary reaction here, which is this fast reversible one, and we need to manipulate that to figure out if we can do some more substitutions. So just remember, the whole goal of all of this circuitous stuff that we're doing here is to somehow make our predicted rate law look the same as our experimental rate law. And the way that we're doing that is trying to use the logic of the fastness or the slowness of these individual steps to rearrange algebraically the individual rate law steps, do some substitutions, cross some stuff out, and hopefully we can get them to look the same. Our first move was to take the predicted rate law that we had here, which was in terms of the disappearance of N2O2, and get rid of that term there. And we did that through this first relationship. We just said, well, that third step is super fast relative to the third one, and so we could make the approximation that the disappearance of N2O2 was roughly the same as the appearance of N2. And so that gave us this new expression down here, but we now need to get rid of this N2O2. So let's go back up to this first fast reversible reaction. Let's see if we can write rate laws for this forward going reaction and the reverse going reaction. Since these are elementary reactions, we can write rate laws directly. So for the forward going reaction of the 2NO, then we can simply just say that we'll just write this as rate, and I'll put an F for forward. That's got to be equal to K1 times NO, and don't forget that's raised to the power 2 because of that species. Since this is an elementary reaction, we know that the rate law can be translated directly from the reaction. That's not true for a net reaction. It is true for an elementary reaction. Similarly, we can write the reaction, we'll just write this for reverse. That's going to be K minus 1, and that is going to be proportional to N2O2 concentration. There's no exponent here because this is a 1 in front of that. Okay, so that's the first step. The next step is to note this part, that this is fast and reversible. Reversible meaning it's so fast the reaction is going in the forward direction at the same rate as the reverse direction. We'll talk a lot about this in the next chapters when we talk about equilibrium. So what we can say about this system is that it is at equilibrium because of the information we've been given, the fact that it's fast and reversible. You would only know this if you were told this or experimentally you deduce this. So we can set these two rates equal to each other because we know that it's fast and reversible. So we can rewrite this as an equality where the forward rate is equal to the reverse rate, and then we can substitute in those actual rate laws to get a new expression, which looks like this here. And remember, we're trying to get rid of this N2O2 feature here, actually in this expression here, because we want our final rate law to be in terms of things that are actually in the overall net reaction. So that's nice, we've got that. So let's solve for that and see if we can then substitute the rest of this expression for that and get it in terms of stuff that's actually in the net reaction. And ta-da, we have now N2O2 in terms of the rest of these variables, and we can see that NO is actually in our real reaction. So let's take this and let's substitute it in here and see what our final rate expression is. Okay, so pause the video, make sure you do this substitution. This is some simple algebra, but it's important to make sure you feel comfortable about this. So this is a whole big thing. What was the purpose of all of this? Well, remember, we had the predicted rate law, which we concluded simply because of the rate determining step. But that rate determining step was in terms of intermediates that aren't in the actual reaction that you would do in the lab. And so we did some fancy maneuvering and some algebra to figure out if we could get this thing in terms of the things that are actually in the reaction, and then see if that overall rate law that we deduce is the same as the one you experimentally deduce. And so the one written here in blue is after all that fancy footwork, and now it's in the appearance of N2 here is equal to 3 of these constants that are multiplied and divided here, multiplied by NO squared, which is a reactant, times H2 concentration, which is a reactant. So that is in perfect form. Let's compare it to the experimentally determined rate law, which is here, which is the appearance of N2 is equal to K NO squared H2. It's the exact same thing, except now we have even more detail in what we just deduced, because this K, which we deduced experimentally, we only can conclude one K, one rate constant. We can't implicitly know from experiment that actually that K is comprised of 3 individual Ks from separate elementary steps. And so now we know that K is actually K1, the forward reaction rate constant for the first reaction, times K2, the second rate constant, divided by the reverse reaction rate constant for the first one. And so these two reaction rate laws are exactly the same. This one now just has more detail because we've actually parsed that net rate constant into its constituent elementary rate constants. And we can say that these two are in fact identical.